I guess it's time to start. Let me share my screen. During the tutorial, you can interrupt me or write your questions, doubts, or any comments to the chat. I will read them. Okay, so let me share my screen. Today, we're going to talk about the 2 pointers. It's a type of technique that we use solve various problems. One of them maybe you already covered in your previous lectures when you merge 2 source arrays. And in that time, you also used a 2-pointer technique to handle the merge operation. However, you didn't give some name for that operation. So this technique basically have a 2 pointers, and we want to move them slightly while covering the entire problem. Let's say we want to merge 2 given arrays, let's say A and B arrays. In that case, if both of them are sorted, A and B are sorted, we want to find a merged array. We want to have a C array that is mix of all elements of A and B, such that C is again sorted. We handled this phase in the merge sort by having 2 pointers, that 1 pointer for each array. For example, that both of them starts at the first, like the beginning of the array, at the first element of these arrays. So we have a pointer for the array A and a pointer for the array B. Later on, we just compare these pointers pointing elements and find the next like smallest element for our resulting C array. Let's say A element is much smaller than B's first element, or let's say pointing elements. In that case, we will just take this element and put to the C array, and we just move our pointer to the next element and continue so until we come to the end for the both array, like our pointers come to the last like end of the array for the both arrays. In that case, we just have a C array sorted, and the time complexity for this 2-pointer techniques is mostly linear in the size of the input. That's the good side of the this technique. Now we will also see some problems that is solvable by using binary search or different techniques. However, when we use the 2 pointers for the certain problems, you can get the linear time algorithm. So here, if the size of first array is n and second array's size is m, we just scan over each of the array's element once. In each operation, we will move one of the pointers to the right. And this scenario, we will just have a time complex of n plus m. This algorithm is already should be familiar for you. You have already covered them in merge sort, and that phase is handled with 2 pointers technique. Now we will come to much interesting problems, and first one of them also kind of exists in your coding practice first, I guess, C problem. So basically, so idea is familiar, but I will make it much easier. So I want to, let's say we have 2 arrays of size of n and m. First array A1, A2, an, B1, B2. And let's assume that A and B are sorted, like non-decreasing, given in non-decreasing order. In that case, we just want to find for each I, or for let's say for each bi, find the number of indices smaller than, let's say, find the number of j's such that aj is smaller than bi. From you, ask it to find this number of j's for each bi. If you want to give example, let's say 1, 2. Also, for simplicity, let's assume all elements here are distinct. If they are equal elements, we can also handle that. We don't have a problem. Let's say 1, 2, 5, 10, 3, 4, 6, and let's say 11. In this case, output should be there are 2 elements smaller than 3, so 2, 2 elements smaller than 2, and 3, and 4. If we do brute force algorithm, for each given I, just try all the j's smaller than bi, we will just end up with a time complex of nm. So basically, for each m, you just run the loop of n, try all of the possible j's. And then if we decide to use the feature of A and B to be given in source order, in that case, for each given bi, we can find the, let's say, not complete the second algorithm. This one's first algorithm, second algorithm. For each bi, find the maximum j such that aj is smaller than bi. If we find this, we can add to the answer and add to the answer j. Why this is correct? When we find the maximal j that is smaller than bi, aj is smaller than bi, we are sure that none of the elements aj plus 1 to an will be smaller than bi because they are given in source order. Hence, aj is the last element that can be smaller than bi in this given source array. So if we know aj is smaller than bi, we also know that all elements in this prefix also smaller than bi. So basically, when we find this maximal j, we can add to the answer all of these elements, like count of them. So basically, that's j. So to find this maximal j, we can just run the binary search because, as we know, arrays are sorted. Like B doesn't need to be sorted here. Just being A sorted fine for us because we run the independent query for each separate BI. In that case, we just have a log n operation, and in total, we just have m log n complexity with a binary search. However, we want to do much better than this, and we can do this for this problem. Basically, we will follow the two-pointer technique. And this two-pointer technique can be explained in this manner. Let's color the given n elements, like A array, B array, with some color, let's say red. These are red elements, and elements in BI are blue elements. Now, if I want to merge these two arrays, same as I do in merge sort, and to have a C array that is concatenation or substitution of A and B, that's again in sourced order. In that sourced array, I can use the advantage of having how many elements smaller than for each blue element. What I mean by that, so basically, let's assume that we have a C array sorted that is repeating the same phase as we do in merge sort. We just find the smallest element and put to the beginning of the C and just continue in that, just move the pointer the next element, and just continue, same as we do in Morse sort. In that case, let's assume we will have a following picture. And we know all of them are distinct. In that case, we can see that for each blue element in this merged array, we can see all elements smaller than this bi lies in the prefix of the C array. Basically, we want to count number of red elements in this prefix from 1 to I-1. Basically, so here, let's say all elements has a array C, so it should be CI. We want to find the number of reds in this prefix. We do this for each blue ball over here, or blue colored element, and we can find the expected answer here, like basically the number of small elements smaller than bi in the A. And this is easy to do. Just follow the same merge sort algorithm. Like, let's say you have a pointer, X pointer, let's say, or we can just say P pointer, Q pointer. In that case, we just do the loop while P is smaller than N or Q is smaller than M. You just do the merge sort operation. If A, P is smaller than B, so we have to also case of when AP doesn't exist, or let's say BQ not exist. So in that case, Q is equal to M, or AP is smaller than PQ. In that case, we need to put elements from the red section. So we just increase the P. Else, when you put the blue element, so this is basically red element, put red ball. And when you decide to put blue element, you just increase again Q, so put blue element, blue ball. However, here we want to sum up, for example, when you come here, let's say you come here, you just have to add to the answer 3. You just say to the result of, if you have a resulting array, result of Q is equivalent to P. What does it say? How many elements are smaller than this? So pointer gives the index, that is the next element in the A. However, this also reveals information about how many elements smaller than B, Q. So again, complexity of this algorithm is linear of the size of 2 arrays, which is O of n plus m. And when you compare it to the logarithmic algorithm, it doesn't show a large effect when n is small, but when this gets bigger, we see the real difference. So yeah, again, we just follow the 2-pointer technique. We have a 2-pointer and each step moving slightly. And in this manner, we just found the all elements smaller than bi in A. And there is a slightly different implementation of this algorithm. Basically, for each blue element, let's take this. Okay, so for each of the blue element, you just iterate from 1 to m. So for, let's say, I from 1 to n. Oops. Okay, for I in from 1 to n, you just have a pointer, let's say p, that starts from the 1. And you, for example, let's say you are in this blue element. Oh, that's right. Okay. I can show on the coding I use. Oh, okay. I need to change my pen. So basically, I can show also different implementation over here. Basically, let's say we have an array of n and m sized, and I will use here vector for instead of the array. Let's say I have a vector of size n and b vector of size m. So I will be having n and m in the first line. Laterward, here, as you might see, I'm using input-output functions from the C instead of using C and Cout. One of your peers asked, how can I optimize my code? I see some of other people's solutions, time executions are much faster than mine. So this can be small trick or hint that to show that C typed input output are much faster than C++ type of input output. And we are lucky to have all functions of C is available to use in C++. So I rather use this in C++ as well. So I'm using scanf for having my input. And now I want to show different implementation of my mentioned algorithm. So for each of them, so here also I used zero index. So I go from 0 to m minus 1. And here I will take pointer that is start from 0. And for each blue element, I will increase my p pointer until the place that AP is not smaller than BI anymore. So what I mean, I will increase the pointer P until it's smaller than my BI. So also we can use here J to not mix up. Let's say I want to increase my J until that place that AJ is not smaller than BI anymore. So also we should bound by the size of the array, so we don't go to the non-existing elements. In this case, after this loop terminates, so basically after this loop terminates, and I'm for answer for the ith element, like how many elements smaller than BI, is equivalent to J actually. So I can say that result of I is J. What does it mean? There are J elements in A array that is smaller than BI. J is zero indexed, and if A0 is already not smaller than B0, let's say, in that case, our J would be still showing the 0th element. So we will just add, it reveals that there are no elements smaller than B0. And when I go to B1, let's say B1 is bigger than A0. In that case, I will increase the J until the place that it will be, like until it will be bigger than B1. So A0 is smaller than B1, A1 is smaller than B1, A2 is smaller than B1. I will increasing. Once, let's say A3 is not smaller anymore, in that case, I would have a J of equal to say 3. That means result of 1 is 3. That means there are 3 elements in A that is smaller than B1. So a result of I keeps the number of elements smaller than bi in the array A. So we can print it. And we'll get the result vector as well here. Yeah, let's run it. What was my test? 4, 4, 1, 2, 5, 10, 3, 4, 6, 11. So as we expected, it was 2, 2, 3, 4. Yeah, each of the element here, each of the element of B array scanned once, and same for the A array, each of the element of A scanned like processed once. So we don't see anywhere J goes back to the to the 0 and come back. I mean, J always increases to the right, so there is no way that we go back in the loop iteration. So even though it might look like it's NM when you glance and just look straightforward way, but this is not the case because each of the element of A and each of the element of B processed once. That is same as you do in merge sort algorithm. So complexity of this one is just n plus m. And to check this, I found a problem in code forces, so we can submit it. It says two given source arrays, and for each element of second array, find the number of elements with less than this. So it's same as our problem. And we can run this test as well. So 1, 1, 2, 3, 4, 6, 6. Yeah, it's same as this. So to see the correctness, we can submit it. This is quite nice educational page of the ITMO. You can find it in code forces. There are some problems that is relevant to binary search. This 2 pointers. If you have free time, I definitely agree. Definitely suggest you to look this place. And as you see, our algorithm passed all test cases. And we can solve more problems. And let's solve this problem. It says that, but yeah, before passing to this problem, maybe I can ask, is there any question about this implementation? Okay, so let's solve another problem that can be solved with the 2 pointers technique. The problem says we have a single array, n elements, and there's no constraint of being sorted or not. We just have just n elements, as each of the elements fits into the integer data type. And we, from us, ask to find the longest segment, contiguous segment in array, such that some of the elements in this array is at most s is given in the input as well. For example, we have s is 20 here. Here, so this is our formalized version. We need to find L and R such that some of the elements in this subarray is smaller than or equal to S. So for example, here, I'm just looking by I. If I take these first 4 elements, some of them would be 15. But if I take this 5th element, at the same time, some will be 21. So that passes my given limit. So I hope you understood the problem. We need to find the subarray with the maximum size such that sum of the elements in this subarray is smaller than or equal to given input S. Let's first implement when you approach some problems to see whether you can, let's say, use the two-pointer technique first. I suggest you to implement the most naive way instead of directly trying to implement the high-level idea. For example, here the naive way would be just try out all ranges and find try out all possible ln errors here in the n square, in order of n square, and later try to find some optimization or try to apply two pointers here based on your implemented brute force algorithm. So let's again input our element, and here I will try all ln errors that starts from 0 to n. Or let's do the inverse. Let's have an R here that starts from, again, 0 to n. However, L would be from 0 to R. And I need the sum between these elements. So let's say I have a sum that traverses from L to R, that finds the sum of the elements. I believe you already seen similar problem of finding the maximal subarray with, I guess, maximal sum of all possible subarrays in the first lectures, and it's similar to that problem. So we just find the sum of this subarray, and if sum is smaller than given S, we should also get S here. In that case, we can update our answer. Answer is the maximal size subarray size. So here, subarray length would be R minus L plus 1. And finally, print our answer. This should be A. Let's run it. And yeah, just a sec. It says 6. It should be until R. Yeah, it says 4. However, this is a cubic algorithm, and you can easily optimize this algorithm with a slight change. For instance, instead of going L from 0 to R, we can go from R to 0 in decreasing order. And in that case, instead of calculating the sum for the L and R every time from beginning, for example, if you have a sum for the range of L and between L and R, and let's say we want to calculate the sum for L minus 1R, as we'll see, L goes from R to 0, so it's going in decreasing order. In that case, we don't need to again calculate all elements sum in this range. Instead, we can just use the already existing sum and just add AL minus 1. So basically, instead of running this entire loop in each ln R, we can have a sum here outside of the second loop and just add sum on the way. So in this way, with a small change of the we optimize our code from n cubic to n square algorithm. Does it make sense? And I hope it says. So in this manner, we can have an algorithm. However, it's again not enough. We can make it much better. Mostly in this two-pointer used algorithms, you can do binary search as well. So here we can binary search the L. And the reason is that sum here is monotonically increasing. So for example, let's say you try the sum of L1. Let's say L1 is some, let's say some L. R. If this one is smaller than S already, you don't need to try the L's in range of L and R. So you don't need to try. So let's say different here. Let's say this is K. So if there is a K that some of them is smaller than subarray sum is smaller than S already, you don't need to try the L. You don't need to try L's in range of K and K plus 1 and R. You can directly go to the other side, like to the 0 to K minus 1 side. And that is shows, because of this is available because of just some array is monotonically increasing as the L decreases. So you can easily, and that's because of all elements of A are non-negative. If there was negative elements, we couldn't decide that, show that they're always increasing. But however, here all sums increasing, so we can just increase them. We continue to decrease our L, and for this part, we can use the binary search to find K, for example, as a middle element between 0 and R. When you find the middle element, you just try whether the sum of the elements between K and R is smaller than S. If it's so, you just go to the left part of this K, like from 0 to K minus 1. If it's not, you go to because if sum is not already smaller than S, there is no way to make sum smaller by just going left part. You should go definitely the right part. So you can easily implement the binary search algorithm to find this L, to find the maximal, or let's say here, minimal L. So I can also implement it actually. So basically, you have a L, let it be low and high. That starts from 0 to R, while low is smaller than high. You'll have the middle element of this binary search. So middle of this range. So this is 1.2 actually. And let it be your L. Okay. And if sum between L and R is smaller than S, then you can easily expand this range. So you should go to the high to the mid. Else, then this subarray is not valid, so you should go to the left part. Sorry, right part. Go to the left part. Mid plus 1. Go to the right part. And here, instead of having, this is L. Finally, when low and high is equivalent each other, then it means we find some L. However, there is a chance that A are already bigger than S. In that case, we cannot do anything. So we will find valid L if AR is smaller than S. So there is a valid L, which is equivalent to saying, so here low and high is equal to each other. So binary search come to the meeting point. And here we can just assume that, or even we can check here, that assert that sum between L and R is smaller than S. So we can update our answer same as we do. This is the case. Here we have a sum part where we need to compute it in O1, like this is possible. So here, not on the binary search idea, we need to also implement the prefix array, like finding the sum between any two like sum of any interval in just constant time. And that can be done in just linear time as well. So basically you will have a prefix array. Let's say it's, and we just do the sum of AI sum. Current sum, and you just compute this prefix array. Laterward, when you want to find the sum between any two range, you can just compute it by just PR minus PL minus 1. So in constant time, you can get the sum of any range. But this is not the case. We don't want to do exhaustive work to just get n log n algorithm. So complexity of this algorithm is n log n. And we can do much faster algorithm by small implementation. That's the beautiful part of using two-pointer technique. So let's skip this part, let's comment it. Okay, and try to implement the two-pointer technique. So good thing about two-pointer, maybe I might have it charged already. Let's try. So here, when we have array, let's say we are here, let's say this is our R. R will go from 0 to n minus 1. When we come to the R, let's say we found the minimal L. We want to find minimal L to maximize the given subarray length to be maximized. So we want to maximize this. For that, we need to find minimal L. Let's say for this given R, we found the minimal L that satisfies the case of sum of the between range, sum of the subarray is smaller than S. And when we move our pointer, so let's say this one is pointer for R and this has a pointer for L, to the R plus 1. So basically you add new element here. So you have a new element that is added, let's say, value of X. In that case, you can still continue to have current L, but definitely not smaller than this L. So you will not have L minus 1 or smaller element for the having optimal L for the R plus 1. Why? Because when we add new element, our sum is only getting bigger and bigger. It doesn't get smaller. So all recall that all elements are bigger than, so all AI are non-negative. So when you add new X here, your sum gets bigger and bigger. So this can either breaks the current condition. So it can be either continue to be smaller or equal to S. In that case, we are good. We already found our L for the R. So it will be same L for the R plus 1 as well. But this is the first case. In the second case, if X plus sum of current, like LR, so here basically X is A R plus 1, A R plus 1. In that case, if it's bigger than S, we should definitely move the L to the right or increase the L. Otherwise, we cannot decrease this current active sum. So there is two things we can say. First of all, there are good L's for current fixed R. Let's say for current fixed R, there are good L's and bad L's, or let's say not good L's. So for current R, in the previous stage, when we found the minimal L that satisfies the case, when this range satisfies, when L satisfies range, we just say it's good L. We just have a, let's say, Boolean artifact that all else in this range are true, like good ones. They are all 1. But all else smaller than this are 0. That means not good else. Now, when you increase your R, when you move to the next R, let's say to the R plus 1, in that case, you can see that the good else are turning slowly. So a new added element, sorry, the single added element here is most probably good L, but for previously good L's started to be turning to the bad L or not good L. So here we can see that these two L's are not good anymore because of just adding new element. So our current active range needs to be configured accordingly. So you need to increase the L. And that means we have a simple framework of having this two-pointer technique for this type of problems. Basically, you will have a R that is always increasing 1 in the outmost loop for R I will write in Python, range of 0 to n. You will have a L pointer that is equivalent to 0 at the beginning, while current sum, let's say, so let's say not sum here. We just say add, first we need to add new element. So when we go to R plus 1, add AR. After adding AR, while range of LR, let's say, while range of AL is not good, then we need to increase L. This is so after finishing this, we just need to check is current, maybe there is a case like this new added element dominated everything and all of them turn out to be 0, 0, 0. So there is no good L that satisfies our condition. In that case, after finishing our loop, we just need to check again, just in case, whether current active ln R is good. In that case, update answer with a range of L to R. This is possible answer for finding the minimum L that satisfies the condition for given R. Here's the small configuration we need to do, like here, just a second. So here current L is not good. Yeah, that's a good. So basically the entire algorithm can fit into this in different problems as well. Of find maximum length range, maximum length subarray. Type of problems can be solved with this framework. So you need to implement here how to add element. Oh, sorry, here we need to also remove AL, then increase L. How to add element, you need to, like, effectively, what I mean by add, how to remove element from current data structure and check whether current added and removed element are good. So you need to check effectively given like active set is good or not. So for example, for the add, so if we come back to the problem that we were solving, the add part, we will just add extra sum variable, and add part will be just like, so sum plus equal to x, and remove part will be just remove the element, sum minus x, and finally good part just checking, let's say, whether sum is smaller or equal to the S. So this is a simple one, like we can just do all operations in just constant time. In this manner, entire complexity will be just linear of the array, because we just have a loop that runs from 0 to n, and L also just runs, like scans entire array once, it doesn't go back, L always increases. So all constant operations are constant, hence algorithm runs in linear time. We'll implement this, and then we will see also a slightly different problem that seeks for finding that goal, it aims to find not maximum but minimum length subarray that satisfies some condition. In that case, we need to slightly change algorithm, but it generally fits for all type of this kind of problems. Okay, and implementation will not take more than 2-3 minutes. As I said, this is simple to code and the most effective way of solving this type of problems. So we just need to implement add, while not good. We just need to remove the AL and increase the L. We just need to add L. And here, if current subarray is good, maybe there is a chance of L needs to be smaller than R. It cannot suppress the L. It needs to always smaller than this. In that case, maybe there is a case like, so here, if L is smaller than R, it means it's already good. So we can check in that manner if you want. In that case, we update our answer. Yeah. So we need to implement these 3 functions, and we will just, okay, let's delete this part. And also, to not have overflow integer, because as we see, 10 power 5 multiplied by 10 power 9 will be 10 power 14. So we'll definitely use the long integer. I will just define some macro that says LL. So I need to have some global sum. When I ask to add some element, I will just increase my X. When I ask to remove some element, we just decrease it. When I ask to find whether it's good, current added and removed, like active set, just need to return whether sum is smaller than X, sorry, S. So here maybe I can give S as a argument. So here I just need to give S. My answer is integer as well. And here, the one part that I'm missing is that S is again given large, long integer. So we should definitely define S as a LL as well. So we should input in special manner in this C. Yeah, I think we are good to go. This is binary search. I commented it. And yeah, this is just linear time algorithm that runs faster than any algorithms that we discussed. Okay, let's try it. We start with cubic and we end up with the O of n algorithm that looks cute than algorithm that we implemented for worse time complexities. And yeah, let's see, accepted. Yeah, I will be also sharing these accepted codes in the canvas so you can track them. Now, just filling the inside of this add, remove good algorithms, we can solve one more problems actually. So here, what does it say? Just arbitrary other problem. I just open it. Okay. It says that find the, okay. Let's solve the one that I discussed to not mix stuff. This one asks to find the shortest good segment. However, this time we define the segment is good if sum of elements in this segment is at least S. So here we don't seek for finding the minimum L. Instead, we want to find the maximal L that sum is at least S. And yeah, today implementation is not taking so much time. So here now we don't have a picture like this. We have a different picture. So here we want to find the maximal L that satisfies the condition. And we can see that here the being good, or let's say goodness, flipped. So here we have now all good L's in the prefix. However, the not good L's is near to R. So we want to find the maximal L satisfies this condition when problem asks to find the minimal interval length. So we define the problem, let's say, find the subarray of L and R such that sum of them is bigger than S, not smaller or equal to S. It should be bigger or equal to S. So here, as the subarray is smaller, we will have a smaller sum, but once we find the satisfying L, in that case, adding new elements will always increase the sum. So all these L's in this prefix will be satisfying the case. So instead, here we just need to, again, here the framework will remain same. The only thing we need to change here is this part. It should be bigger or equal now. The part that we need to change here, so this one was the finding the maximal thing. Now we need to change slightly this algorithm. Let's cut it to make it work for the minimal one as well. So let's delete it. If we want to find minimum length subarray for a given condition, what we have to do, basically, so yes, here should be L. We continue to add AR, that's okay. But whenever we increase L, whenever not, A is not good. We increase, so currently, let's say for fixed R, this range is good. And whenever you increase your R plus 1, we are seeking for the maximum satisfying L. If L plus 1 is satisfying for new R plus 1, we want to increase it. So here, only change, we just want to change that. This is not good. Instead, we just say, if it's good, we continue to increase it. If it's good, we just continue to remove AL and continue to increase. But there is a chance that, let's say, current segment is good, and we remove the AL. Now we ask for the AL plus 1 to the, let's say, so we are just found the maximum L. For the R, now we want to do the same for the new element. We added R plus 1. In that case, it says that L is good. So we just increase the L. Now L plus 1. However, we don't know whether L plus 1 to R plus 1 is good. In that case, but if there is a chance that L plus 1, R plus 1 is also good, we need to continue to increase it to L plus 2. We just delete it, remove it. But whenever we find the not good range, in that case, we need to stop and just one element before that will give me good range. That is my guarantee. So basically, while in the previous algorithm we're increasing while the current range is not good to find the satisfying L. Here, like to find the minimal L. Here we want to find the minimum length subarray, so we want to find maximum L for each R. So we just increased while it's good, increase L to find the maximum L. Whenever this is not good, the L minus 1 to the current R should be good set. So here we just need to check, L minus, so basically our L needs to here decrease. I couldn't do that. Second. So after loop ends, you just need to, so after loop ends, you just need to decrease the L minus one once. So you just set one element before that. So this is the small slight change that you will discover between finding minimum and maximum, and both runs in linear time. This will just go back n times, and this is not big deal. So you process each element twice here, 2n, and when we calculate order of n, it's again linear in the size of array. So to find the minimum length subarray, that sum is at least s, as we do, we just need to change the first of good condition. Good condition becomes now bigger or equal. And here we need to include slight change to the algorithm. So we increase if it's good. If it's good, increase, increase. When we find not good L, L minus one should be good. So here, decreasing L minus one will give me the good subarray. There is a chance of current, like there is a chance that L might be smaller than 0. So let's say you add new elements, but when you add all elements, again, sum is not smaller, not bigger than s. In that case, you need to accept that there is no L satisfies my condition. So when L is smaller than 0, it means we couldn't find any subarray that is bigger or equal to s in the sum. So if L is smaller than 0, it means we didn't find any L for current error. But if it's the opposite, it means we found L. And let's run the algorithm. It says 5. However, we want to find minimum here. So our answer starts with n, let's say. There is a chance that all elements sum not enough for me as well. In that case, I will start with an n plus 1. If after finishing entire algorithm, my answer is again n plus 1, in that case, I need to print minus 1. It says if there's no such segment, prints minus 1. So we'll just print minus 1. Else, it means I found answer. Let's run it. Okay, let's print all error. It says 4 to 0, 1, 2, 3, 4. When we try 4, its sum is 21, so it's good. When I come to the okay, so when I come to the 6th element, some of them is already bigger than 20. So n should increase while sum is bigger than. So we just add it, and we just continue to increase L while. Oh, okay. Here we forgot to, when we come to the back, one step back, we need to add that, add back that element, because we just remove. When we just go one step back, we need to add it back to the data structure. And it's 3. And again, as I said, it's 2n, and again, linear time algorithm. Hopefully it will pass in first attempt. Oh, we have runtime. Let's see. What's the problem? Our sum is bigger than integer, but we handled that. Oh, okay. Yeah, I think like this means that L is -1, but this shouldn't be the case. So we should do something smarter here. If like don't try to add non-existing element. If L is bigger than 0, it means there is an answer. So we can decrease 1, add that element, and update our answer accordingly. Minimum answer R minus L plus 1. If L is 0, it means that there is no satisfying segment, so we just don't touch that at all. So I hope you will understand this after thinking a little bit. So current segment of L to R is not good, but L minus 1 R is good. So we just decrease the L1 by 1. However, when L is 0, it means there is no way to make this segment good. So we don't do anything. Our current active pointer will just stay wherever it is. Otherwise, we just move 1 back. Actually, we don't need even to go back. So let's submit this one. This algorithm has a complexity of 2n, but I just think of way to not go. You don't need to go back. You can just update the answer accordingly. And because in next iteration, if currently LR is good, in next step, I will add more element and I will increase L again. There is no point to add this, like decrease it and add it. It passed, as I said, but I can make it just linear of n, like O of n, not without any constant. By just removing this part, I can just say L minus 1 R is good. So I can update here in just +2 manner. So this should do the same thing as I do. Let's test it. Yeah, so finding minimum and maximum differs by a little bit, but the main part of implementing this idea of coming from implementing these 3 functions effectively. For example, for this problem and this problem, you can I can give it in the references. You can definitely give a shot. So it asks to find the number of, by the way, it passed. Number of subarrays. Instead of finding the maximal and minimum, it asks to find all possible subarrays such that number of distinct elements in the subarray is smaller or equal to k. So the good thing is about finding the maximal L for each R will give me or help me to find all possible subarrays count. How? You just find the maximal L for given R. In that case, you can be assured that all L's in 0 to this found maximum L already satisfying the condition. So you don't need to count them one by one. You just answer this else value. In that case, you can find out all good subarrays. So I definitely suggest you to solve this problem that seeks for the distinct numbers in given range, and also this one that asks us to find the number of good segments. As I said, that condition here differs by maximum element in this active like segment minus minimum element is at most k. So difference between maximum and minimum differs by k. So that remains on your task that you need to effectively implement add, remove, and good conditions here. So you can both get accepted for both problems. Not in linear time, but a little bit more than this. However, much better than any algorithm that exists for this problem.